Hello, Math 1090 students. Today I would like to start looking at section 5.2, logarithmic functions. In section 5.1, we set up and use exponential models to make predictions. However, you may have noticed that solving exponential equations was not discussed. The reason is simple. None of the algebraic operations we have discussed are sufficient for solving exponential equations. For example, consider the equation 2 raised to the x equals 10. To solve such an equation requires the use of logarithms, which we will present now. A logarithmic function is a function that can be represented in the form f of x equals log base b of x. Notice that when I read this, I call this base b, where the base b is always greater than 0. The logarithmic function is not defined if b is 0 or if b is a negative number. The logarithmic function, log base b of x, is defined to be the function that undoes the exponential function, f of x equals b raised to the x, where here the base b we'll recognize from section 5.1. Technically, we call these functions inverse functions. For example, consider f of x equals 2 to the x and the related logarithmic function log base 2 of x. When we talk about the related functions, they will always have the same base. Log base 2 of x has the property that if 2 raised to the 0 is 1 in exponential form, that log base 2 of 1 is equal to 0. If 2 raised to the 1 is 2, then log base 2 of 2 is 1. If 2 squared is 4, log base 2 of 4 is 2. If 2 cubed is 8, then log base 2 of 8 is cubed, or sorry, is 3. Graphically, we can see the relationship between the exponential function 2 to the x and the logarithmic function base 2 as reflections of each other around the line y equals x. So here I have a graph of y equals 2 to the x, and the graph of the related logarithmic function log base 2 of x. Notice that 2 to the x goes through the ordered pairs 1, 2, which is here, 2, 4, which is here, and 3, 8, which is here. While the graph of log base 2 goes through the ordered pairs 2, 1, 4, 2, and 8, 3. Furthermore, the domain and range of the two functions are related as follows. The exponential function 2 to the x has a domain that's all real numbers, negative infinity to infinity, and a range, the y values on the graph, that are always greater than 0. While the logarithmic function base 2 has a domain, x values that you can use are only positive numbers, but the range, the y values, are all real numbers, going from negative infinity to positive infinity. The equivalent statement for logarithms is what we use to evaluate logarithms. Every logarithmic function, or every logarithmic statement, log base b of c is equal to a, is equivalent to some exponential statement. Notice that for these both statements, the base b is always the same. So the base of your logarithm and the base of your exponential. And the answer to a logarithm, a, is always going to be the same as whatever the exponent is on your exponential. Let's use this equivalent statement to evaluate the following logarithms. What is log base 5 of 25? To answer this question, I usually put a question mark here. Log base 5 of 25 is something. What is that something? It's going to be an exponential. It's 5 raised to what power is 25? Some students will remember this as a triangle statement. The base of your logarithm raised to the other side equals this argument right here. Now, in an exponential form, we should be able to evaluate 5 raised to what power is 25? Well, it has to be 5. Nope, I almost wrote 5. 5 raised to what power is 25? Let me grab my eraser tool. Five raised to what power is 25? It has to be 2. Let's try another one. 6. Log base 6 of the square root of 6. This has to equal something. What is that something? Well, to answer this, we rewrite it as a related exponential. It's always the base raised to the other side gives this argument here. So I write this as 6 raised to what power is the square root of 6? Using what we know about exponents, we know that if the exponent is 1/2, then 6 raised to 1/2 is the square root of 6. Log base 3 of 1/3 equals something. What is it? Well, it's going to have to be the base raised to the other side equals 1/3. So 3 raised to what power is 1/3? Again, using what we know about exponents, it has to be -1 because 3 raised to the -1 power is 1/3. Now I'd like to give you a moment to work on the next example yourself, these 3 problems here. If you could, please pause the video, look at these 3 examples, and after you're done, come back and verify that we get the same answers. Let's look at the solutions to these. Log base 4 of 64 is asking the question, 4 raised to what power is 64? And if you're not familiar with some of these exponents, you can use your calculator to help. Imagine 4 raised to the first power. That's 4. 4 raised to the second power, 16. 4 raised to the third power, that's 64. So here we know the answer. Log base 4 of 64 has to be 3. Log base 3 of 243 is asking 3 raised to what number is, not 343, three raised to what number is 243? Again, I'll try some things on my calculator. I know that 3 squared is 9. 3 cubed, 27. 3 to the 4th power, 81. 3 to the 5th power, that's the 243. So here I want to know that log base 3 of 243 has to be 5. Log base 7 of 149 is asking 7 raised to what power is 149th? And from one of our last examples, we knew that 3 raised to the negative 1 is 1/3, and this produces our fraction, but we don't want 1/7, we want 1/49th, which leads me to think, what if I did 7 raised to the negative 2? Notice this gave me a decimal. I don't want to see the decimal version of this. My calculator will convert this to fractions. I'm assuming yours will too. On my calculator, you hit the math key. Option number 1 turns this to a fraction. And that's the 1/49th, which allows me to say that log base 7 of 1/49th has to be negative 2. Some logarithms get used more often than others, and so now we present what is referred to as the common and the natural logarithms. The common log is a logarithm where the base is always 10, and it is usually written in the form log of x. Notice that they do not explicitly tell you that the base is 10, like we did on these other ones, log base 7, log base 3, log base 4. If they don't tell you the base, it's safe to assume the base is going to be a 10. Another way I could have written this, but we do not write this generally, is this is log base 10 of x. But like I said, we don't write the base 10 if it's base 10. We just write log x. The natural log is a logarithm where the base is e, and it is typically written as just ln of x, or natural log of x. Again, we don't write the logarithm explicitly this way, but I could have written this as log base e of x. But when talking about logs base e, we generally just write natural log, or ln of x. Let's practice these with some examples. Evaluate each logarithm. What is log of 100? So again, this is asking the question, 10, the implied base, raised to what is 100? And we know 10 squared is 100. So log of 100 is 2. Now you can confirm this on your calculator. You do have a log button on your calculator. Notice your log button on your calculator is just log. And if I were to type in log of 100, this will give me an answer of 2. How about log of 1000? Well, log of 1000 would be 10 raised to what number is 1000? Again, if you're not sure, you can try your calculator. You could try guessing what the exponent is. We know 10 squared is 100, so 10 cubed would have to be 1000. So the answer to this question, what is log of 1000? It has to be 3, because 10 cubed is 1000. What is the log of 1/1000th? Now again, from previous examples, we know that when you raise a base by a negative number, like -2, it produces a fraction. So maybe we can ignore the fact that it's a fraction and just ask ourselves the question, what is log of 1000? And then add the negative exponent to make it be a fraction. Specifically, this is asking the question, 10 raised to what is 1000? And this has to be -3. The inverse property of logarithms. By the definition of a logarithm as the undo function of an exponential function, we explicitly give the following inverse properties of logarithms. That says whenever you have the log base b of an exponential base b, that the log base b and the exponential being inverses, these two functions will always undo each other, leaving as an answer just the value of whatever the exponent is. Similarly, if you have an exponential base b of a log base b, this would also be just x. Let's practice this with a couple simple examples. What is the natural log of e to the negative 3? Again, because natural log and the exponential base e are inverses of each other, these will cancel. This is just negative 3. E to the natural log of 3. Again, you want to think of these as inverse functions. They'll cancel. This is just 3. What is log base 3 of 3 to the 4th? Again, thinking of these as inverse functions, these will undo each other. This ends up being just 4. Another property of logarithms we want to be familiar with is the change of base formula for logarithms. This says that every logarithm of any base b can always be written as a quotient, a division, of two other logarithms. For example, log base b of a can always be written as the quotient of log of a divided by log of b. Notice that this is two different logs. I also could have said log base b of a is the same as natural log of a over natural log of b. It turns out both of these two expressions are equivalent, and this tells you it doesn't matter which logarithm you use. You can use a log base 10, or you can use a log base e. Let's practice this with some examples. Evaluate each expression using the change of base formula and your calculator. Log base 3 of 5. Notice your calculator doesn't have a log base 3 button. You have a log button, which is base 10, and a natural log button, which is base e, but we don't have a log base 3 button. So using the change of base formula, we can say log base 3 of 5 could be written as log of 5 divided by log of 3, or you can write it as natural log of 5 divided by natural log of 3. Now on your calculator, I'll calculate both of these so you can see they're the same. Here we'll have log of 5, make sure you put parentheses around that, divided by log of 3. And notice this produces the decimal approximation 1.46. Similarly, we could have did natural log divided by 5 divided by natural log of 3. So here use the natural log e, 5 divided by the natural log of 3. When using your calculator, make sure you put the parentheses around your argument so that your calculator is clear on what it's evaluating. Notice this also produces the same decimal, 1.46. I'd like to give you a moment to try the second example, log base 2 of 9. If you could, pause the video for a minute and work this on your own, and then come back and check and make sure we get the same answer. Let us evaluate this expression now. Log base 2 of 9. Using the change of base formula, this would be natural log of 9 divided by the natural log of 2. I could have used base 10. I generally like using natural log because there's less letters to write. There's just 2 letters where log has 3 letters. Not really a good reason, but it's the reason I use. Now using our calculator, this would be the natural log of 9. Notice I forgot my parenthesis. You arrow back. Natural log of 9 divided by the natural log of 3. And this comes out to be 2. Oh, I think I did that wrong. I typed in natural log of 3. I should have typed in natural log of 2. Let me try that again. Natural log of 9 divided by the natural log of 2. And we get a decimal approximation. I'm going to go 2 decimal places and call this 3.17 as an approximation of this. Now again, the way you think of this is this log base 2 of 9, this is asking the question, 2 raised to what power is 9? Well, we know 2 squared is 4, 2 cubed is 8, 2 to the 4th power would be 16. So this answer has to be between 3 and 4. And specifically, we're saying 2 raised to the 3.17 is approximately 9. And I can confirm that on my calculator. 2 raised to the 3.17. This is approximately 9. It's a little bigger than 9 because remember we rounded this. It wasn't really 3.17, it was 3.1699. Let's look at another property of logs. Here we're going to talk about the 3 properties of logarithms that allow us to rewrite logarithms as equivalent logarithmic expressions. They're referred to as the exponent property, which says anytime you have a log base b of an exponential, you can always move the exponent, the r, in front of the logarithm. The sum property that says the sum of 2 logarithms that have the same base, they must have the same base, can be rewritten as the log of a product. The difference of 2 logarithms that have the same base can be written as the logarithm of a quotient. Make sure that the first one goes on the top and the second one goes on the bottom of your fraction. Let's practice this with the next 3 examples. Write the following as a single logarithm. Now I do recognize that there's a sum here, and I will end up writing it as a product. But with my formula, we're not allowed to have coefficients in front of our logarithm. So the first thing we'll do is we'll use the exponent property, which says I can move these 5 and this 3 as an exponent. And write this as log base 8 of x to the 5th plus log base 8 of x cubed. Now that we've written them without coefficients, we can use the sum property that says this can be written as log base 8 of x to the 5th times x cubed, which using rules of exponents, we can write this as log base 8. Remember, x to the 5th times x cubed. When you multiply 2 exponential expressions that have the same base, we add the exponents. Now I have 2 more examples here, and I'd like to give you a moment to do these on your own. If you could please pause this video again, take a moment to evaluate or rewrite these logarithmic expressions as they're asked. After you're done, unpause the video, and let's make sure we get the same answers. Let us proceed. Write the following as a single logarithm. Here we want to use the difference property that says when you have the difference of 2 logarithms, you can write this as log base 4 of a quotient. Remember, the order is important. The expression that appears first has to go on the top. And the second expression has to appear on the bottom. And while this is correct, I do ask that you simplify this and write this as log base 4. And you see 12 divided by 3 would be 4. x to the 8 divided by x to the third. Remember, you think of this as having 8 x's on top. Make sure I get all 8 of them here. 1, 2, 3, 4, 5, 6, 7, 8. Divided by x cubed, that would be 3 x's. Notice that these x's cancel, leaving just 5 x's remaining, and they're on the top. So it'll be 4x to the 5th. In general, remember, you can just subtract your exponents. Last example. Write the following as the sum or difference of logarithms with exponents written as coefficients. Now, after you practice a couple of these, you'll probably be able to do these in a single step. But for this example, let's work it out in pieces. The first thing I notice is that we have a division. And so I want to write this as log of something minus log of something. Remember, the first expression is the one that's on the top. The x to the 16th, the y to the 11th, minus log of z to the 6th. The second thing I notice is that this product can be written as a sum. So I can write this as log of x to the 16th plus log of y to the 11th minus log of z to the 6th. Now, using the exponent rule, this will be the last thing we can do. We can take each of the exponents that is in our problem. The 16, write it as a coefficient. The 11, write it as a coefficient. The 6, write that one as a coefficient. So I'll end this as 16 log of x, 11 times the log of y, minus 6 times the log of z. Now, by itself, these properties is nothing that somebody is going to stop you on the side of the road and say, I'll pay you $5 to rewrite this logarithm as the sum or difference of logarithms. However, this type of, or these types of calculations are required when we want to solve equations. Let's look at a couple examples. Solve the following equation for x. I'm going to do this first one, and then I'm going to leave the second one for you. To solve for x, we first recognize 5. Well, let's see what we know. We know 5 squared is 25, and this is too big. And 5 to the first power we know is 5, which means x has to be a number that's between 1 and 2. Now, how do we find it? Well, when we have 5 to the x equals 23, I want to figure out what x is, and I'm going to use the property of logarithms that allows exponents to go in front. To do that, I first must apply a logarithm. And let's take the natural log because it has less letters to write. What you do to one side of the equation, you do to the other. Now written like this, we can say that we can use the exponent property that says the natural log of something raised to an exponent allows the exponent to go in front. So this is the same thing as saying x natural log of 5 is the natural log of 23. We wanted to figure out what x is, so let's get x by itself and divide both sides of the equation by the natural log of 5. This will give us our final expression that says x has to be the natural log of 23 divided by the natural log of 5. And we can find a decimal approximation of this on our calculator. The number will do natural log of 23. Make sure you put the parentheses to end this numerator, divided by the natural log of 5. And we get back a decimal approximation. I'm going to write it to 2 decimal places, 1.95. Notice that this result is approximately what we thought it should be when we said x had to be between 1 and 2. Now, the next example is very similar to this. I'd like you to work this one on your own. If you could please pause the video, work this on your own, and then come back and check and make sure we get the same answer. Let's go ahead and evaluate this expression. Again, if you're trying to get just a guess of what this answer should be, we probably would acknowledge that we know 2 cubed is 8, while 2 to the 14th has to be 16. And this tells us that whatever x is, it has to be between 3 and 4. How do we get there? Well, to solve the equation 2 to the x equals 10, I want to get that exponent x out of the exponents. And so we choose to apply a natural log to both sides of the equation. Again, we could use a logarithm base 10 or a log base 3. It doesn't matter. I choose to use natural log because there are less letters. This allows us to use the property that this exponent can go in front of the natural logarithm. And we can write this as x natural log of 2 equals the natural log of 10. We want to get the log or the x by itself, so we divide both sides by the natural log of 2. This allows us to write x as natural log of 10 divided by the natural log of 2. We'll use our calculator to get a decimal approximation of this. And we come back with the decimal approximation. I'll write this to just 2 decimal places again. This is approximately 3.32. Notice that this is what we thought it should be. The 3.32 is a value that we thought would have to be between 3 and 4. Let's try some more complicated equations. Solve the following equation for x. Here I'm just going to jump right to applying logarithms. So if we think about how to apply this, we have e to the 3x is equal to 25. We are going to apply the natural logarithm to both sides of the equation so that we can use the property that logarithms allow exponents to go in front of the logarithm, and write this as 3 to the x, not equals, my eraser tool is not working very well. Try that again. 3 to the x natural log of e equals natural log of 25. We want to get x by itself, so let's divide by the things that are not x. We'll divide by 3 natural log of e on both sides. This will allow us to see how this 3 will cancel this 3, and the natural log cancels the natural log. leaving just x on the left-hand side as natural log of 25 divided by 3 natural log of e. And we can put this directly in our calculator, but I'd like to point out that in this expression, we should know what natural log of e is. Remember, this is saying e raised to what is e. The base written to what gives you this answer, this input. And we know this has to be 1. So technically, natural log of e is really 1. This allows us to simplify this expression as x is natural log of 25 divided by 3. Our calculator tells us this will be natural log of 25 divided by 3. Again, make sure you put parentheses to tell the calculator what the argument is. As a decimal approximation, I'll write this to 2 decimal places. Let's write it as 1.07. Let's look at some application problems now. The value in millions of dollars of exercise treadmills bought from China can be approximated by this function, where x equals 0 corresponds to the year 2000. In what year did, or will, the exports reach 5.4 million? Here we're being asked to solve the equation, when is, for what value of x will 0.8208 e to the 0.0927x, when will this eventually reach 5.4? This is an equation that requires the use of logarithms. Now in this problem, our goal is to figure out what x is, what year that'll be. So let's first divide both sides by the 0.8208. This will give us e to the 0.0927x is equal to, and let's see, 5.4 divided by this 0.828, 0.8208 gives us approximately, and I'm going to go 4 decimal places to avoid rounding. Oh, that doesn't look right. Oh, I typed in 0.54. It should be 5.4 divided by 0.8208. There we go. And I'm going to write this to 4 decimal places just to avoid rounding error. This would be approximately 6.5789. Now, again, to get x out of the exponent, we are going to choose to apply a natural log to both sides of the equation. Then we can use the exponent property that allows any exponents to go as coefficients of our logarithm. And we can write this as 0.0927x natural log of e equals the natural log of 6.5789. From our last problem, we know that the natural log of e is really just 1, so we don't really need to write this. And to get x by itself, I'm going to divide both sides by the 0.0927. So we can say x is going to be the natural log of 6.5789 divided by the 0.0927. And I'd like you to check this on your calculator, make sure this works. Natural log of 6.5789 divided by 0.0927. 0.27. This gives us an answer of 20.32. This would be 20.32 years after the year 2000, which tells us that exercise treadmills will reach 5.4 million in the year 2020. Or technically 2020.32 of a year, but it'll be in the year 2020. Now, the next two examples are very similar to the one I just did, and I'd like to give you a little bit of time to work these on your own. So again, if you could please pause the video and solve both of these equations. After you're done solving them, come back and verify that we are going to get the same answer. Let's look at a solution. The value of a car is depreciating according to this model. Notice again that the base b being less than 1 tells us that we're talking about a decaying exponential model, where v is the value of the car t years after it was purchased. When will the value of the car approach 15,000? So here we're being asked to find a value of t such that the 18,000.85 raised to the t will get down to 15,000. Now we want to solve for t, so let's first divide both sides by the 18,000. Now you can get a decimal approximation now if you like, but I'm going to leave it as a fraction. This division would result in the equation 0.85 raised to the t is the 15,000 divided by 18,000. I'm then going to choose to apply a natural log to both sides so that we can use the property that logarithms move exponents as coefficients. This will give us the equation t natural log of 0.85 is equal to the natural log of 15,000 divided by the 18,000. Then to get the t by itself, we'll divide both sides of this equation by the natural log of 0.85. This will give us t has to be the natural log of 15,000 divided by 18,000 divided by the natural log of 0.85. And we'll use our calculator to evaluate this. Again, use parentheses as necessary to make sure you're grouping things correctly. This is natural log of 15,000 divided by 18,000, parenthesis to close the first logarithm, divided by the natural log of the 0.85. This gives us the value I'm going to go 2 decimal places again, 1.12 years. It'll take 1.12 years for an $18,000 car to depreciate to $15,000. Let's look at the next example. How long will it take an investment of $13,000 to double if it is invested at 6% compounded monthly? Now, from our previous homework, we want to remember that the compound interest formula would give us A of t, the balance in an account, is going to be your starting balance, the 1,300, times 1 plus, remember it's going to be your interest rate 0.06 divided by the number of times you compound per year, which we're doing monthly, so 12, raised to the 12t. We're being asked to determine when this $1,300 is going to double. Now, it's going to double when it has reached 26,000. So we're being asked to find the solution to the equation. When this 1,300 will reach 2,600, when it'll double. And we want to solve this equation for t, to find the value of t that does this. So an exponential equation. Now again, to solve this equation, we want to get t by itself. And so let's start by dividing both sides by this 1,300. This will give us 1 plus 0.06 divided by 12 raised to the 12t equals 2. We can choose to apply a natural log to both sides of this equation so that we can use the exponent property that says that this exponent 12t will go in front of the natural logarithm. And to help simplify this, I'm going to do some rewriting along the way. The 1 plus 0.06 divided by 12 ends up being 1.005 equals the natural log of 2. And we want to get t by itself, so let's divide both sides by the thing that's not t, divided by 12, natural log of 1.005. This will give us t is equal to the natural log of 2 divided by 12 natural log of 1.005. Now, when you put this in your calculator, you must be explicit and let your calculator know that this 12 natural log of 1.05 all appears in the denominator, and you're probably going to have to use parentheses here. So here we go. Natural log of 2 divided by parentheses to start your denominator, 12 natural log of 1.00, oh, too many zeros, 005. One parenthesis to close off the logarithm, another parenthesis to close off the denominator. This gives us the year 11 point, I'm going to round to one decimal place, 11.6. This tells us it'll take 11.6 years for a $1,300 investment to double and reach $2,600. Okay, I have two more examples for us to look at. These last two examples are very algebraic and reminiscent of what we would see in a traditional college algebra class, where we are asked to solve for x. Now, to solve for x, we want to recognize that there is x in both of these logarithms. However, using properties of logarithms, we can say that anytime that we have the sum of logarithms, we can write it as a product of x times the x plus 3 equals 1. It'd probably also simplify things a little bit if we chose to rewrite this product and write it as log of x squared plus 3x, where I've chosen to distribute the x into the parentheses here. Now, this logarithmic equation looks like some of the logarithms we started with. where I want to rewrite this logarithm as an equivalent exponential expression. Remember the way we did this is we said the base raised to the other side has to equal the argument. This was similar to when I asked the question, what is log base 2 of 8? And we said, well, to answer this question, it would be 2 raised to the other side equals 8. And we said, well, it has to be 3 because 2 cubed is 8. So we use that same property here. Now remember the base, although it's not written, is explicitly 10. So this is saying 10 raised to the other side has to equal x squared plus 3x. Now remember 10 to the 1 is just 10. And so to solve this quadratic equation, remember we looked at back in, I think it was chapter 3, we want to solve quadratic equations by setting them equal to 0. So let's subtract the 10 to bring it to the other side. We could use the quadratic formula to solve this, but we should recognize that this is factorable. We're looking for two numbers that multiply to negative 10 and add to 3. We can factor this as x plus 5 times x minus 2. This gives us two solutions, either x equals negative 5 or x equals positive 2. However, both of these are not solutions. They could be, but in general, one of them is probably not going to be a solution, and so we have to ask which one is the solution, which is not. Remember, one of the properties we stated earlier for a logarithm is that the domain is only positive numbers, meaning you can never take the logarithm of a negative number, which tells us that negative 5 can't be a solution because when we do the log of negative 5, which is not in our domain. So the only solution that we have is 2. That's going to be our only solution. I have one more example for us to look at. Again, I would like to let you work this on your own. So if you could pause the video, work this one on your own, and come back and check the answer after you're done. Let us look at the solution now. Now I want to solve this equation for x, and the first thing I'm noticing is that we're taking the difference of two logarithms. Remember that the difference of two logarithms is always going to be written as a fraction, a quotient. This would be log of the quotient x plus 5 divided by x plus 3 equals 1. To solve this logarithm, we'll rewrite it as an equivalent exponential. Remember, it's going to be the base raised to the other side equals this argument. Now the base, although not written, is a 10. So this would be 10 raised to the first power has to equal the x plus 5 divided by the x plus 3. Remember, 10 to the 1 is just 10. Now this equation is a little more tricky because we have a fraction where the x is in both the top and the bottom. And to solve a problem like this, what we want to do is cross multiply. Multiply to get this x plus 3 on the other side of the equal sign. You could also think of this as multiplying both sides by x plus 3. Where when you multiply by x plus 3, on the right-hand side, these x plus 3's both cancel. And so it just leaves the x plus 3 on the right. Excuse me, on the left. With what's left, we have this x plus 3 times 10 has to equal x plus 5. Let's proceed by distributing, multiplying the 10 into the parentheses, and write this as 10x plus 30 is the x plus 5. To get x by itself, let's subtract this x from this side to give us 9x. Let us also subtract 30 from both sides to get, I think that's negative 25. And if we want to get x by itself, we divide both sides by 9. This tells us x is going to be negative 25/9. Now you're probably thinking that can't be a solution because it's negative. And like in the last example, we said negative 5 wouldn't work. However, we want to be cautious. This does not end up violating the domain of our logarithm. Recognize that negative 25/9, so negative 25 divided by 9, gives us the decimal. It's approximately negative 2.77. Notice that when we plug in negative 2.77 into this logarithm, negative 2.77 plus 5 is still going to be a positive number. Negative 2.77 plus 3 is still going to be a positive number. So we're not violating the fact that we know the domain is only positive numbers. We do not take the logarithm of a negative number with negative 2.77. This tells me that this is our solution to this logarithm. Now, this is the last example I had for you in chapter 5.2 logarithms. So I'm going to end this video now. It got a little bit long. It's almost 56 or almost an hour. So I'm going to stop this one here. This will be the end of chapter 5.2. This will give you everything that you need for your homework. I hope this is helpful.